All right, guys, so this is our last topic in our circuits unit, and this one we're returning to something that we discussed before when we were studying energy and work, and that is power. So, as I mentioned before, the reason why the current moves in a circuit is because we provide it with energy, and as it goes through resistors and other, such things, some of that energy gets used up, and so the rate that the energy is used is called the power. Remember, power is the energy used or the work done divided by how quickly or essentially the time that it takes to do that work or dissipate the energy. So because this is fairly common, usually when we think of like wattage, we think of light bulbs or computers or electric appliances. I want to take this time and show you guys how we can calculate the power being used in a circuit. So just like with Ohm's law, there's a very simple equation that related voltage, current, and resistance. The same thing happens with electric power. So if we know what the total voltage drop throughout a whole circuit is, so like from one side of the power supply to the other side of the power supply, and we know the current that travels through the circuit, we can calculate how much power that power supply would have to supply. In other words, how many joules per second or watts it would have to produce. We can also do this for a resistor. So if we know the voltage drop, the drop in voltage across the resistor, and the current passing through the resistor, we can calculate the power being dissipated by the resistor in the form of heat or light. And the equation that allows us to calculate this is very simple. It's P, and this is for power. So this is my power in watts, or joules per second, is equal to my current, I. So this is current. This is in amps, times, again, the drop in voltage across my circuit or across my resistor, depending on what I want to know the power of. So this is voltage, and that is obviously in volts. So we have this simple equation, P is equal to IV, or PIV. Just as you do with Ohm's law, if you guys don't want to do a lot of math here, we can make our little triangle of greatness, and we can have P is equal to IV. So if you want to, whatever you want to calculate, you just kind of cover that up and it shows you how to calculate. So if I want to calculate voltage, I would cover up the V and I would say, oh, okay, well, that's power divided by current. If I wanted to calculate current, that's power divided by voltage. If I want power, it's current times voltage. So our little triangle of greatness can be used for this just as it could be for Ohm's law. All right, so that was usually used, P equals IV is usually used for a whole circuit. Whoops, my computer crashed. Sorry, let's see if I can get this going again. Slideshow. Okay, sorry about that, guys. Okay, so that was for a whole circuit. For a resistor, what happens is the current will pass through it, and as I said, some of the energy that, some of that voltage that it had before the resistor, some of that's going to be used to kind of push the charge through that resistor. It's kind of like pushing against friction in a way. And when it does that, just like in friction, some of that energy is going to be changed into heat or possibly light. Light bulbs are essentially resistors, and what they do, if you have like one of the filament lights, is they convert all that electric energy into heat, but also into light. And so maybe we want to know that. Maybe we want to know for a resistor how much power, how many joules per second of heat or light are going to be produced as we pass current through it at a certain voltage. And to do this, I'm not sure how mathematical you guys want to be about this, but we're going to start with this, P equals IV, and we're going to also remember Ohm's law is V is equal to IR. So I can replace this V over here with this equation, and that gives me P is equal to I times IR. So for a resistor, if I know the current through the resistor and I know the resistance, I can calculate the power, the heat, the joules per second being dissipated using this equation. I could also say that I is equal to V over R, and I can replace the I over here. And so now this will become P is equal to V over R, because I replaced the I with this, times V. And so this gives me P is equal to V squared over R. So this is another equation. Maybe you don't know the current going through the resistor, but maybe you know the voltage, the drop in voltage across it. You can use this equation to calculate the power being dissipated by the resistor. So these two are very useful when you're kind of focusing on a resistor. Not that you can't use P equals IV for a resistor, it's just a lot of times in these problems, if you know the resistance and you know the current or the voltage, you can still calculate the power. So that's what these are used for. Now, a neat little application of this is how the power company, the electric company, has to take this into account when they deliver power to our house. So we have our little, our little power plant, and it's creating the power, and then you have your house over here. Okay, so you have your house over here, and there's all these lines. This could be like miles and miles and miles away, and then let's just pretend like you have telephone poles. I think a lot of your neighborhoods, they probably don't now. But you have all these lines, and they're wires, and they have to be delivered to your house. And this could be like miles and miles apart. And so the question is it better to transmit this at a to transmit this power, because again, P is equal to I times V. So we can transmit a certain amount of power, a certain amount of joules per second, with a high current and a low voltage, or we could transfer it at a very high voltage but a very low current. The question is, okay, well, which one's better? Well, we're going to turn to this equation. Okay, P is equal to I squared R. This wire is actually our R. We do not have superconducting wires going from the power plant to our house. Okay, there is a resistance. If you have miles and miles and miles of wire, there's going to be quite a bit of resistance to it. And so what they do is they have they transmit this with a very, very, very low current. Okay, and the reason why is because this voltage across this whole thing is going to be very high, but there's not going to be a big change in voltage going from here to here. So the two equations we have for resistor, one is V squared over R. This change in voltage as you go from here to here is actually quite small. Okay, so this could be like at tens of thousands of volts, but it's going to be tens and thousands of volts essentially across its length. So this change in voltage as you travel through the wire will be very small because it doesn't take a lot of energy to get through that wire. However, if we had a high current, okay, we would be heating up the wire. So what they do is they transmit the power to us at extremely high voltages but at very low current. And what that does is it reduces that energy that you're paying for, essentially, that heat from heating the wire and being dissipated into the air. Having said that, the wires still do heat up. There's a reason why birds like to sit on wires, especially in the winter. It's because they are kind of warm. These wires do get a little bit warmer. So anyway, so I thought this was a cool application of electric power and kind of the consequences of it. There's not a big change in voltage going across this wire, so if we can have a very high voltage, as long as there's not a big change, our power is not going to change all that much. But if our current was high, it would just really heat up these wires, and it would waste a lot of the energy that's being created at this power plant. Okay, so here's a problem or a scenario, a question perhaps, that I would like you to consider for the next class. And I'm going to ask you guys this at the beginning of class. I want to hear your answers for it and why. So in this we have 3 bulbs. So these are light bulbs. They're arranged in series, connected to 120 volts total. And they have different power ratings. Now these power ratings are essentially always standardized to 120 volts. So if you put 120 volts across this one, it's going to dissipate 100 joules per second. This would dissipate 25 joules per second. This would dissipate 50 joules per second, but they're in series. So I'll let you think about the consequence of that when it comes to the voltage drop across them. And the question is, which one will be brightest and why? And I'm going to want to hear your answers at the beginning of next class. So think about it, come up with an answer, and I'll be interested to see what you say.